Good morning, everyone. So, today our topic is pulse coded modulation. So, what is pulse coded modulation? Pulse coded modulation is used to convert an analog signal into a digital signal. What does it basically means? So, basically, it means if we have an analog signal, if we have an analog signal, maybe of just like this, and here is an amplitude and it is the time. So if we converting an analog signal into a digital signal, so basically that the process we means is the pulse coded modulation. Here we get the output in a coded form or in a binary output. Like how this the process occurs basically, in pulse coded modulation, basically we first need to do sampling to convert the analog signal into a discrete signal. So basically this is the discrete signal where we basically breaks the analog signal into small parts. Then we do quantization to convert discrete signal into a digital signal. Discrete signal into a digital signal. After that we do encoding of that digital signal. And basically there is also a note, if high frequency component are there at the analog input, then we should use the low pass filter at the input before we going to signal, before we giving signal to sampling. So basically first of all we know about the block diagram of pulse coded modulation. So the block diagram is just going like this. Here is our analog signal. First we do sampling where we break the analog signal into discrete parts. Then after getting that discrete signal, we will we will do the process of quantization, where we what is the basically the process of quantization, we'll learn about that in the upcoming slides. For now just know that after sampling we'll do quantization. Then after quantization there is a process of encoding. This process we also know in further slides, so just skip it. This is the process of encoding, and after that we'll get the digital data. And this is also a detailed structure of or a block diagram for the process of pulse coded modulation. So here's basically the source of the analog signal. Here's the low pass filter. Why use the low pass filter we have mentioned here. And then we do this, use the sampler, then the quantizer, then encoder, and here we get the binary output or the digital data. And then again the process of this is the process of transmitter. Then there is another process of transmission path, then how the transmission occur from one end to another end. Then we got the receiver end, where we finally receive the signal, then again decode it, then reconstruction the filter, and the destination, what is the source, we get the similar output. So this is the receiver end, this is the transmitter end, and this is the transmission path through which the signal transmits from one end to the another end. So basically this is the process of pulse coded modulation. So why use the pulse coded modulation? So there are certain benefits and also some demerits also. We will learn them in the further slides. So basically this is the process of or the block explanation of the block diagram for the pulse coded modulation. So in the next slide we are going to learn about the quantization process, quantization of the signal. So what is quantization? So quantization of an analog signal is done by discreting the signal with a number of quantization levels. So this statement doesn't make any sense without knowing about the basics of what is quantization. So here we know about some basic facts about quantization. So what is quantization? So quantization is a process of rounding off of approx. Means if we have just like if we have 5.9 5.19, then we approximate it to 5.2. So likewise, when we get a analog signal, we'll take a part of an analog signal, then we have to take the approximate values, approximate values or approximate points or approximate quantization levels to determine the actual digital code, because it is not possible to take each of the data, otherwise it will increase the bit size of the data, and it is and for that we have to increase the bandwidth also. So we take the approximate values to determining the signal. Rather than taking each point, we will take the approximate quantization level points to determine the signal. It will makes little bit error, but we have to choose between whether we want to increase the bit rate, which was is more important for us, whether it is important to maintain the bandwidth or it's the bit rate, or we can deal with little bit error also. So this is the thing. So this is the quantization process. If we see this diagram, this is the basically the part of the analog signal. Here I will take three quantization levels, 1, 2 and 3. And now if we and what is this points? This is the quantization points, as I mentioned above. If we connect these points in this way, then it will give another signal. So basically quantization points, and there is another term of step size also. So basically we'll know about this also. So basically this blue line is this point is a continuous messaging signal, which is also an analog signal, and this a red point is the quantized signal. Okay, and and if we mark these points also, the black points, then what are they? So they are the step size. So how we know about the step size and what is step size? If we try to get an idea about that, so step size is the highest voltage point minus the lowest voltage point, and Q is the quantization level. So here's the process of quantization process, where we have the step size. This is the formula, and for all values of xt, what is xt? Is the continuous time messaging signal in range of delta 0. We'll know about the delta 0, what is delta 0 output Q, and similarly Q1, delta 1, delta 2, and then at center step message, step means s by 2. We'll know about these things in the slides basically. So here's the thing. So this is the quantization process. As I explained, quantization is a process of taking approximate values. Here's the diagram. If we know a little further, going a little further, so this is basically the lower point, these are the higher point. As we know about the step size, so what is step size? Step size is basically the upper end minus the lower voltage point by whether how many levels are there, 1, 2, 3. So basically it's 3. So for each step size, what is the value for that? It's 1 centimeter. So in that way we'll get the value of the step size. Okay, so this is the process. This is the process of quantization basically. So if we take a bigger part of the signal, this is basically the bigger part of the signal. What are the deltas? Deltas is nothing but the difference between these values and these values. As we see, we have taken approximate values of the voltage levels 0, 1, 2, 3. Just like similar, these are the difference between these points. Delta 1 is difference between these points, and delta 2 is difference between these points. Okay, then how to assume the value of the quantization levels? The value of the quantization level is just nothing but the half half of the value of if the difference between these levels is s, then we will take the quantization level value is the half of this level. This is s by 2. So we'll take the value in this path, and this is the first quantization level q0. In the similar way, for the next delta 1, the quantization level q1 is the half of this point, so this is there. Then q2 will be here, and q3 is here. So after marking each of the points, we will going to connect them, and after connecting them we will get a signal, different signal, approximate signal, which we will going to convert it in a digital code. So basically we can take another example. So this is the example. So here if we take a analog signal just like that, so this is the analog signal, and now we will do the process of sampling. So this is the process of sampling where we sampled the signal. Then after doing the sampling, we will do the process of quantization. Then we'll mark those points, and after marking those points we'll get the grid like structure like this. So then after that, as we said, we will take the these are the points. What are these points? These points are the quantization level points. Then how we'll get these points? We'll take the approximate values. Like this point, we'll take the approximate values point, when we'll take the approximate values of the point. So if we take the point on that, if we get the point here, if we get the point here, then we'll take the approximate point at here. If we get the point here, we'll take the approximate value here. If we take here, if we get the quantization point here, then we'll take the point here, and after connecting each of the levels, we'll get the structure like that. So for here there is no movement of the graph, so the value is 0. So we'll take the value for this is 0 0. This is just the binary number for the value 0. Then after that there is a graph up, and if we connect this line to here, we get the value of 1. So we'll get 0 1 as the binary value of 1. And after that the graph again ups again, and here the point is a little bit upper than 2, but as we taking the quantization value, so we know we'll take in quantization, we'll take the approximate values, so we'll take the value around 2. So this is the point, and for 2 our binary value is 1 by 10, so we'll take that value. Then after again we'll up again, and there is the value of 3. Then again 1 1. Then again we see the graph is again getting down with the same values of quantization level values. So again there is 0 1 0, 0 1 and 0 0. So basically this is the process where we understand the quantization points and quantization values, and how this actually occurs. So there are few points we can understand. Quantization is representing the sampled values of the amplitude by a finite set of levels, which means converting a continuous amplitude sample into a discrete time signal. So basically we have already understood these things, so just skip it. Both sampling and quantization results in the loss of information. Yes, how this happen, we'll learn about that in this thing. The quantity of quantizer depends upon the number of quantization levels used. Yes, of course, if we use more number of quantization levels, then basically these parts are related to the error in the quantization process. So what is the error in the quantization process? This is basically the thing. See, if this is the analog signal, and this is the quantization points, and after connecting the quantization points we get a signal. But basically if we see the difference between the original signal and the path created signal, is there are the black points here. So these are nothing but the errors. This terms as the error, because these things will create little bit of difference, or difference between the original signal and the assumed signal. So In the similar way, if we take the getting in this statement, both sampling and the quantization results in the process in the loss of information. While do sampling, if this is the analog signal, then we will cut the analog signal into small parts. In this process there is a loss of information. In the similar way, in the process of quantization also, we will not take the error parts, we'll take approximate parts, we'll take little bit of error in it. So likewise this statements explains self-explanatory now. So here are step size decreasing. If the step size decrease, so the number of intervals q increases. What does it means? If the step size decrease, then we to connect these dots we need to increase the number of intervals, so quantization error is less. As we see here, the as the number of intervals increase, so we'll, after taking also the approximate value, our approximate value is more likelier to be the mean value. But if we take long gaps, then the error size is more. If the error size is more, then basically it is take a wider difference between the original value and the slide taking value or the approximate value. So here the step size increases, so the number of intervals decreases. As the step size increase, number of interval decrease, so the accuracy also decrease. Basically we can also use the term of accuracy here. If the if we take after for determining a value, if we'll take small values, just like if there is a value needs to come like 5.1923549, just like that. If we take up, okay, just forget about the example. I think this don't take so long, it don't have the content, it don't have this much content to understand for that long. So basically this is the term, this is the error. If we go further in the term of quantization, then we can understand another thing, that is if the number of q increase. What is q? Number of intervals. Number of interval increases, then bit rate also increases, bandwidth also increases. But if we decrease q, then also these things are decreases as they are directly proportional. But if we decrease q, then what is the problem? If we decrease q, step size increases, means accuracy decreases. If accuracy decrease, then there must be a far wider difference between the original signal and the getting signal. So that's completely depending upon our choice, that what thing matter for us, whether it matter whether we need accuracy or we need the more, we need accuracy or we need the bandwidth. We need to make a choice between them. So we are talking about bandwidth for a long. So what is bandwidth? Bandwidth of a pulse code modulation. Let the quantizer use the V, number of binary digits, to represent each level. Then the number of levels that represented by V digit will be Q equals to 2V. This formula we already seen in the previous slides also. If we see that here, just like, yes, just I think I don't explain these things, but okay. So just get back a little. Why q is important? Like that, q is equals to, take, just assume, if we assume like if q equals to 8, means 8 intervals, 8 quantization levels, means 8 voltage values. Okay, how many bit to represent 8 voltage? Then there's the formula of q equals to 2n, where we'll put this, and then what is the value? Then we need 3 energy levels, 3 bits to represent 8 voltages. Okay, likewise this is the formula also, where we have the q, where we have 2, and where what is this? Comment down in the below. So of course I'm just explaining the same thing. The number of bit per sample, this is the number of bit per sample is V. The number of samples per second is Fs. Number of bit per second equals to number of bit per sample into number of sample per second equals to V bit per sample into Fs sample per second. The number of bits per second is also called signaling rate of PCM and is denoted by R. Signaling rate PCM equals to R equals to VFS, and basically this is the basic formula of bandwidth. So if we compare these two formulas, then basically we get the transmission bandwidth of pulse coded modulation. Here's the evolving formula. If we take the BW bandwidth is lesser equals to 1.5 R, then what is the value of R? We'll put that value, then this, then after more calculations, then we'll get the end result. Bandwidth is lesser equals to VFM. So what are this Fs and what is this FM? I think you know about that, this basics. Okay, last topic, signal to quantization ratio in pulse coded modulation. In the signal to quantization ratio, SQNR is a key metric used to evaluate the quantity of a pulse code modulation system. It measures the ratio of the power of the original signal to the power of the quantization noise introduced during the quantization process. A higher SQNR indicates better signal quality with less distortion due to quantization. The signal to quantization noise ratio is the defined as the, this is basically the formula. So what does the signal to quantization noise ratio do? It indicates the better signal quantity with less distortion, but due to quantization. Due to quantization, how signal quality improves and how it's less in distortion. That helps me to know about those things. So these are the basic things. So this is the noise to quantization ratio. So it is a type of a signal at input. What is xt? Already explained. Is known, then it is possible to calculate signal power. So this is the noise power. The number of bits V and quantization level Q are related as. So these are the basically the relations. We need to learn those things for the numerical purpose. This is the expressing of the signals to noise ratio in decibels. The equation shows that the signal to noise ratio of quantizer increases exponentially with increase in bit per sample. So this is the video. This is the overall pulse coded modulation, where we explain everything about the pulse coded modulation, its bandwidth, its quantization, its block diagram, basic block diagram, and the basic process. So thank you.